All right, hello, welcome back. So in the previous video, in the previous videos, we saw rotation matrix and 9 element description, Euler angle, 3-element description, and axis angle. It was a 4-element description of rotation. And because of that extra one variable that is in Euler, I'm sorry, is in axis angle, the description doesn't have the issue of singularity or gimbal lock that was in the 3-element Euler angles. This video is about a slightly different version of the four parameter description, also work of Euler, and it is called Euler parameters. It is very similar in concept and everything, except with a slight mathematical differences that makes it somewhat easier to work with, at least in computations. So again, it's a four this is M parameter what am I writing? Description of rotation. It is defined as follows. So you have 4 parameters, usually shown as epsilon. Epsilon x is ax sine of phi over 2. And remember, this a and phi are our axis and angle description. I have epsilon y, you guessed it, ay sine of phi over 2, epsilon z, az, z, sine of phi over 2, and a fourth one, eta, which is cosine of phi over 2. Slightly different shape, but you run out of a, so you have to do something. And the good thing, or one of the features of this description, is that the norm of these 4 parameter set is 0. So ex squared plus epsilon y squared plus epsilon z squared plus eta squared equals 1. So essentially, it is the same axis angle description, slightly written differently, leads to this nice property, I would say. And because of that, a slight change of way you show the parameters, it has interesting and good properties. So one thing, a few notes or definitions. There is something called this Euler. Where do you put the dash? Euler 3 vector. So that one is kind of 4 vector. This one is 3 vector. It is a vector epsilon, which is epsilon xi plus epsilon yj plus epsilon zk. And if you look at the values, it is actually the same vector as a, only scaled by values sine of pi over 2. So these epsilons actually represent the direction of the axis of rotation. So it has a kind of nice interpretation to it too, but only scaled with the size, with how much you're rotating. Excuse me. Let me think. And because of this kind of definition, it doesn't have that ambiguity in defining A if there's no rotation either. If your angle of rotation is 0, you can, without any other assumption, fully define these epsilons and eta, so Euler parameters. Nice kind of twist to the same concept to make it better behaved. So again, as before, if you know the Euler parameters, you can go to, I don't know, rotation matrix and other forms of description and vice versa. So let's look at rotation matrix. If you want to go with these Euler why is it so difficult for me to write it? Parameters to going back and forth. So epsilon x is 1/4 eta R23 minus R32. Your epsilon y is 1/4 eta R31 minus R13. Epsilon z is 1/4 eta R12 minus R21. And remember, these R's are number, R12, 21, 32. These are the elements of the rotation matrix R, big R. And eta is 1/2 square root of 1 plus trace of R. That is the sum over the diagonal elements of rotation matrix. So this is, if you know your rotation matrix, you can easily calculate the Euler parameters. And because these Euler parameters are almost the same concepts, almost, as the axis and angle parameters, going the other way takes a similar form. So I have kind of these two symmetric and skew symmetric parts, and I add them together. I'm just going to write the end results. So it is 1 minus 2 times epsilon, that I'm writing it in matrix form, transpose times epsilon. So this is just a scalar, times I3/3 plus 2 epsilon times epsilon transpose. So this one is this one is a 3/3 matrix minus 2 eta epsilon tilde, and this something tilde when epsilon is a vector. Remember that this epsilon tilde is a skew symmetric matrix that is 0 minus epsilon, what is it, z, epsilon y, epsilon z, 0 minus epsilon x, minus epsilon y, epsilon x, and 0. And here is how you can get, if you know the Euler parameters, you can get the rotation matrix back. And last thing I wanted to say is kind of a good benefit of having these forms, at least compared to Euler angles, and to some extent, not a lot, to axis angle parameters, is that you can more easily combine successive rotations. So first you rotate about, I don't know, this axis that amount, and then about the another axis a certain amount. How can you combine those to find the final rotation? So to do that, in Euler parameter sense. So let me do it for 2 and then for more than 2 rotations, successive rotations. So epsilon x, epsilon y, epsilon z, and eta. And these are my final rotations, or not final, let's call it total. Total rotation after 2 consecutive rotations. The first one, I'm going to put it here. Epsilon x1, epsilon x y1, epsilon y1, epsilon z1, and eta 1. Why is it not good enough? So this is my first rotation. And for the second one, I'm going to construct a big 4x4 matrix using the Euler parameters of the second rotation. Along the diagonals, I have all etas. And I don't know where it comes from. Ask Euler, but it works. Ez2 minus E, let me write it a little further, minus EY2 EX2 X2, sorry, this is not good. EX2 minus EZ2. This is also an almost a skew symmetric matrix, but instead of the diagonals being 0, the diagonals are etas. And E epsilon x2 epsilon y2 epsilon yz, I'm sorry, y2 epsilon x2 minus epsilon z2 minus epsilon x2 minus epsilon y2 and minus epsilon z2. And these are from the second. What did I write? Second rotation. So you can construct this matrix and multiply by the vector, 4 vector of your first rotation, you get the total rotation in the end. And you can extend it for many. So this is your final rotation. You can have, do this. Let me do this. This is your first one. You multiply it by this big matrix. For the second one, you multiply it by the third rotation and so on. So we can always pre-multiply all these 4x4 matrices to figure out what is your total rotation. You can also do it for just two rotations, rotation 1 and 2, in a vector form. So in vector form, your epsilon vector is eta 2 epsilon 1 plus eta 1 epsilon 2 plus epsilon 1 cross epsilon 2. And your eta is eta 1 eta 2 minus epsilon 1 dot epsilon 2. So something fun to notice here is that because of this cross product, the order obviously matters, as we discussed before. The order in 3D rotation, which when you order first and when you rotate first, then the second matters, and it shows up in the cross product, and that changes your total axis of rotation. But the angle of rotation is independent, something independent of the order, something interesting to think about. All right, so there is one last 4-parameter description of rotation called Quaternion. I didn't find a good resource. I'll try to find something and also post something on that. Quaternions are very useful. They are a very elegant math. They are, you can think of it as a 3-dimensional extension to complex numbers. Interesting. And they are kind of the go-to method when you are, well, analyzing and working with especially IMUs, when you have some measurements in local frame, some measurements of angular velocity in local frame, and you want to track the motion. Quaternions become extremely useful in that kind of application. Essentially, you keep multiplying all your quaternions that you have had so far, and that gives you the final orientation of, I don't know, your phone or any other device that has these inertial measurement units in them. I'll try to find something fun to post, but there won't be a video by me about that. All right, so that is all I have for now. We saw 4 different versions or types of describing rotation in 3D, how we can relate them together. And in the next sets of videos, in the next modules, we'll be looking at angular velocities, and finally, how we can relate those to the topics of dynamics. All right, until then, happy studying.